All right. Excuse me. So we have talked about several reactions, and we left off Wednesday, talking about oxidation of alcohols to carbonyls. Today we're going to pick up right here because, as you can see, it's kind of like a progression. We went from reactions of alcohols to oxidation of alcohols to carbonyls, and now we're going to talk about today how some reactions of carbonyls. There we go. All right. So we're going to talk about some reactions of carbonyls. And the next section with the amines is kind of similar because amines react with carbonyls. And so we'll see some of that as well. Excuse me. But let's go to the first reaction, right? It's called the Wittig reaction. And it is a way to convert ketones and aldehydes into alkenes. So let me show you, let me just take the aldehyde. All right, so I'm gonna take that aldehyde. And I'm going to show you kind of a shortcut way to think about this first. And then I'll show you how the actual mechanism works. Right, so this is here. And if you notice the reagents, I'm going to point out the reagents. You need, this is how you know you're doing a Wittig. All right, you need an alkyl halide. I'm just going to start with this alkyl halide. You need triphenylphosphine. This is the dead giveaway right here. When you see PPH3, that's a dead giveaway that you're doing a Wittig reaction. And then you also need a base. You also need a base, KOH. That's not the only base you could use, but that's the most common. So here you can see, let me show you the shortcut, and then I'll show you the mechanism. So the shortcut method is to look at the alkyl halide, right? And you can see that the alkyl halide has this structure. Right, so if that's my alkyl halide, let me just put that down here. All right, so the shortcut method of thinking about this is to take the alkyl halide and subtract out one hydrogen and the halogen, right? Is because the carbon of the alkyl halide is what will eventually replace oxygen in the carbonyl. So if I take off one hydrogen and the halogen, I'm left with this, right? I'm not putting a charge, because that doesn't really exist. I'm just showing you what's left over. Right, so it's this right here that's going to replace oxygen. And when we say convert a carbonyl into an alkene, right? Again, this is drawing on your knowledge of functional groups. So now it's going to be here, CH2. That's one of your products. That's the main product. Right. The goal of that reaction is to turn a carbonyl into an alkene. All right. And then there's some other side products that we'll talk about as a consequence of the mechanism. So you'll get this product. This is actually the driving force of the reaction. Because you form that P, the phosphine oxide, that P double bond O bond. Very strong bond and very energetically favorable. So that's actually what drives the reaction. And then you'll have whatever your base is. Of course, you're going to get water if we use KOH. And let's say, for the sake of argument, KBr. So the KOH, it was the base. Use that. Obviously, you're going to have a proton transfer in there somewhere. You made water, and then the counter ion from the base is going to end up with bromine. All right, so let's go through the mechanism. It's actually a three-part mechanism. And the first step of the mechanism is Aldehyde formation. So an Aldehyde is like what we call another term for it is a Zwitter ion. It's just a species that has a positive and a negative immediately adjacent to each other. And I'll show you how that happens. That's the purpose of having the alkyl halide. So let me show you that. So in the Aldehyde formation, that's where your alkyl halide, in this case, is CH3Br. That's going to react with triphenylphosphine. And this is just a simple SN2 type substitution. Where this is going to come here, kick off the bromine, and then you end up with this. Right, this phosphonium salt. And this is not the Aldehyde. It's just a precursor. That's why you need a base. So the base is going to be here. All of this is taking place in the first step. Right? So the base will come in and do proton transfer here. And these electrons are going back to carbon like so. So you're going to end up with CH2. That's negative. This is PH3. That's positive. This is your Aldehyde. Plus water plus KBr. All right. Any questions about that part? So you attack again, even though we're doing new reactions, this is not new stuff. This is the same stuff we've been studying since part one, nucleophile, electrophile chemistry. The phosphorus in this case acts as a nucleophile, the alpha halide is the electrophile. And the second part of that process is acid-base chemistry, right? The proton on that carbon is acidic, and the base comes in and rips it off. So then you get your illet, and you form that. This is your illet is a reactive intermediate. So that's what's going to react with your carbonyl. Right? And then you can also draw illet this way. With a double bond between carbon and phosphorus. Both of those depictions are accurate. You can draw it either way. Right? This one has no charges, and then in the top you can see the two charges are adjacent to one another. All right. So now once we get to past that step, and this is something I like to talk about this in terms of actually doing it. If you were in a lab, you would set this up and go to lunch. I say this every time I teach this part. You set this up, you go to lunch, and then you come back and take a syringe of whatever your carbonyl is. And again, you're running this at maybe -10, very low temperature, -10, -20. You go to lunch, you come back, and you start syringing in your aldehyde slowly so it can react with the illet, because that's the next step in the reaction. So now you have your illet, and then that is going to react with your carbonyl. And this is only one method. This was the original method for converting carbonyls into alkenes. There are many innovations on this method using the same type of technology where you take an illet and react it with a carbonyl. There are several different derivations of this reaction, many analogs of it. All right, so I'm gonna take that illet right here. And I'll put the electrons up top this time. So that now is going to react with, I'm going to draw the carbonyl upright, the aldehyde upright. Let me actually put it this way. Right? So now what's going to happen here? What do you think? Give me your best estimation based on all the knowledge you've attained from part 1 and part 2. You have a carbonyl, which we've already talked about having on multiple occasions, having a huge dipole towards oxygen, and carbon being partially positive, oxygen being partially negative. We talked about that. And we have a negatively charged carbon. Give me your best hypothesis as to what's going to happen right here.
Will be carbon on the, is it the illet?
Say that one more time. You kind of your audio is kind of choppy.
Is it the carbon on the illet?
Okay.
Will attack the carbonyl carbon?
So like this?
Yeah.
Yes. All right. So there's some debate about this. This happens, the attack happens, but there's some debate about the intermediate, what the intermediate actually looks like, whether it's what they used to call a beta-ene. I'm going to show the beta-ene for clarity. But there's been a lot of research done that shows that the beta-ene doesn't really exist. It's actually some type of cyclic intermediate or cyclic transition state, and then like a electron transfer that way. But I want to show the beta-ene first, just for clarity. All right. So when this happens, let's write this out. So here's my carbon from the illet. Here's my carbonyl carbon. That's a hydrogen here. There's my alkyl group over here. And now this is here. That's negative. And then I have my 2 hydrogens here. and then this phosphorus here, right? This is the bond that got formed when the illite attacked the carbonyl. And that eventually that's what we want, right? Because the product that we're trying to get to is an alkene. And so the first step to making that is to make that sigma bond between those two carbons. All right. Anybody not see that? So the other proposed mechanism or the proposed mode of attack for the illite on the carbonyl is like this kind of like a puckered 4-member transition state where you have this here, and then your illite is, let me change the color on that. Your illite is here, with this being the CH2, and that's like a partially formed bond here, and then your phosphorus is here. And that's like a partially formed, a little like a coordinate bond between phosphorus and oxygen. So it's like a kind of like a 4-member cyclic transition state, and then you just transfer your electrons that way. And this is what the standard thought is now as to how this reaction happens. It used to be that it was believed that it went through this beta-ene intermediate, which is right here. But after, further people do, that's why people do research, right? The more research you do, the more answers you get to. Or sometimes you find out that what you thought was real really wasn't. And so after doing multiple studies on this reaction, it was determined that the beta-ene didn't exist. There was no, you couldn't detect it by any means, NMR, no spectroscopic means could you detect the beta-ene. But I like showing that because it makes the reaction, it gives you a lot more clarity as far as the reaction is concerned. So let me just box this in. So this is the proposed transition state for that attack. All right. So let's go back to the beta-ene, and I'm gonna show it. I'm gonna show it this way because it makes it easier for you to think about it. Because the other transition state is kind of beyond the scope of the class. So now the beta-ene, and this is again based on the classic mechanism. The beta-ene now cyclizes. All right. So now this has been proven and been detected. This intermediate, which is a 4-member intermediate. So you have P, O, and then my carbons are here, right? That's my alkyl chain right there, right? So this is what we call oxophosphate. And this intermediate right here is what eventually decomposes to give you your alkene, right? So you have, first you make the illite, you go to lunch, you come back, you but slowly add in your aldehyde using a syringe or a syringe pump. And then now you have this oxophosphate intermediate that comes from more than likely this transition state right here. And then from that intermediate, you generate this oxophosphate. And now this is where the reaction, this is the final step, which is decomposition of that. right? So that decomposes. So now when we look at this, how can we get a pi bond here? Uh-oh, wrong pen, sorry. How can we get a pi bond there? What can we do? No, nothing external. Everything is internal. So what can we do to put a pi bond there?
Resonance.
Okay, we could kind of think about it like that, but in order to put that pi bond, we don't really have electrons that are free, but we have bonds that can be broken, right? And so when we think about this, if we take this and we break this bond, that pair of electrons can be used to make my pi bond. And if we break this bond, that pair of electrons can be used to make the pi bond between phosphorus and oxygen. So in the end, we get these two products. All right, we have this CH2. All right, so that's again, to keep in mind, this is the same carbon from that aldehyde, and this is the same carbon from the ylide. So that's that plus P double bond O pH3, right? And this right here, believe it or not, even though it's a side product, the formation of this, what we call a phosphine oxide, the formation of that is actually what drives the reaction. Making that PO double bond is highly exothermic. It's a very strong bond, and the goal of any reaction is to go from weak bonds to strong bonds. So anytime you do that, then your delta H is going to be negative. That's going to make the reaction exothermic, and it's also going to drive the reaction. So it make the reaction happen even faster, right? Because the activation energy is going to be lower. All the stuff that is connected to being exothermic in nature. Lower activation energy, negative delta H, negative delta G, all the stuff we learned in part 1, right? So the phosphine oxide is actually drives the reaction, right? That's even though it's a side product, the formation of that double bond between phosphorus and oxygen is a very powerful motivator for this reaction to happen, right? So you can do the Vidic reaction on any ketone or aldehyde. If you want to use an ester as your carbonyl source, then you have to use a different method. There are some reactions where you can actually use an ester as your carbonyl. There are other reactions where you can have different types of ylides, like the Clark-Steele reaction. There's a bunch of different types of ylides that exist, all based on this original technology of making a phosphorus ylide and then reacting it with a carbonyl to get an alkene. All right, questions about that? No, that was a lot, but any questions about the mechanism, about the arrows, about what's the nucleophile, what's the electrophile, anything? Right, so when you see this reaction, right, what you're looking for, again, if you make flashcards, what you're looking for is the triphenylphosphine. That's the giveaway. The triphenylphosphine and with an alkyl halide. When you see those two things together in the presence of a carbonyl, it's a dead giveaway that it's going to be a Vidic reaction. So let's go down to the reactions we were doing, and let's work on this reaction right here. All right, because in the first reaction, we talked about it on Wednesday, right? We took that alcohol, we oxidized it with chromic acid to the carbonyl, up to the aldehyde. Now we have an aldehyde, we have an alkyl halide, triphenylphosphine, and KOH. What do you think the outcome of that reaction is going to be? Right, we're going to convert that aldehyde into what?
Alkene.
An alkene. This is important right here. All right, you see the alkyl halide here. I want to make this like really plain and clear. Like I showed you the shortcut method on purpose. The temptation a lot of times with this reaction in the time that I've taught this class is to try and stick this carbon right here in the place of oxygen. You can't do that. Look, it's always the carbon that's bonded to the halogen. So it's got to be this carbon, right? Because it's this bond that you're exploiting when you make your ylide. So it's never the other, it's always the carbon attached to the halogen. So if I take my shortcut method, I'll see that if I subtract out HBr, HBr, then I end up here, right? And this is what ends up replacing oxygen, this carbon right here, right? I have to take off one of the hydrogens because if I don't, and I stick that on there, it's going to have too many bonds to carbon, right? So what would that product look like? I'm just going to cheat and steal it. All right, anybody? What is my alkene going to look like? It's going to have that carbon right there. Same carbon from up top in the place of oxygen. All right, anytime you're doing a acidic, that's what happens. You take a carbonyl and you convert it into an alkene. So that's another example of a acidic reaction. All right, questions about anything so far? About the acidic, about the ylide, about anything?
I have a question.
Go ahead.
Okay, so when we convert the aldehyde to the alkene.
Uh-huh. Go ahead, I'm listening.
Never mind.
Oh, you got it. You figured it out.
Yeah.
You had a light bulb moment. Good. All right. Any other questions? All right, let's see if we can finish this reaction wheel out. And I'm going to go back because we'll have time. I'm going to go back and do acetal and hemiacetal formation. We'll do that. And then we're going to do epoxide opening. Because we know how to make epoxides from part one. We just haven't talked about how to open them up. So let's finish this out. We'll come back to this reaction right here. But let's see if we can figure that out. What kind of reaction is that? And let me give you a hint. So you're doing it in the presence of an acid, H+, and you have an alcohol and a carboxylic acid. What do we get from that? Anybody? This is one of the first reactions we talked about in this section.
Is it Transistorification?
Yes, thank you. It's a Transistorification. And again, let me just make this like really plain, right? You have a alcohol and you have a carboxylic acid. right? You can see the functional group. Anytime you're doing transistorification, this is what you're doing. You're taking the alkoxy part of the alcohol and swapping it. It's not that simple because it's an addition followed by an elimination. But even if you don't know how to push the arrows, you should be able to predict the product, right? So this is a transistorification, and let me see if I can go out. I can steal that. Uh-oh. There we go. Right, even if I don't know the arrows, I can predict the product. I should be able to. Right, so it's the transistorification. So in this case, the alkoxy part of the alcohol is just going to swap out with the hydroxyl group that's on the carboxylic acid. Right, it'd be that plus water. Right. So again, even if you don't know how to push the arrows, you should be able to predict the products. And the arrows are a consequence of knowing the difference in a nucleophile and an electrophile, because all these reactions operate off the same principle. Right, so nucleophile reacting with an electrophile or acid reacting with a base. And there's a very fine line between nucleophiles and bases and acids and electrophiles, very fine line. Yeah, so let's go back to here. I'm going to steal this. We've got 10 minutes left. All right, so here, this is an example of another reaction of carbonyls, and it is the formation of what we call a hemiacetal and an acetate. Right? Notice these two are derivatives of each other. The only difference is the stoichiometry. To get the hemiacetal, it's 1 mole of alcohol plus a carbonyl, a ketone or aldehyde. Now, this is different, and don't get this confused with esterification, because that uses alcohol as well. But here, this has to be a ketone or an aldehyde. Because if it was an acid, then it would be transistorification. All right, and the outcome is, again, let me show you what happens. So you can see the alkoxy portion of this is in blue, and that ends up attacking the carbonyl. So let's go through that mechanism, because this is probably, out of all the arrow pushing we'll do, this is the simplest of all of it. So let's do Hemiacetal formation. And I know this might seem arbitrary, but these reactions are pretty powerful, because acetals and hemiacetals are ways to protect carbonyls. Like if you're doing a total synthesis, you're making this big giant molecule with biological properties, anti-cancer properties, antifungal properties, whatever. And you have a step in that reaction where you need to touch a functional group, but the method that you're using may also touch a carbonyl that's free. And so sometimes you need to protect your carbonyls. So you'll cover them up or mask them. And this is one way to mask them, is by turning them into hemiacetals or acetals, because it takes away their reactivity. And then you can always go back at the end and reverse the process. All right, so let's take ketone here. We're just going to react this with the alcohol, right? The ketone is electrophilic. That big dipole going from carbon to oxygen. So that's partially positive. So that's going to come and attack here. All these reactions that we're talking about in this section, the carbonyl is the electrophile. All right, so that's coming there. It's going to give me this intermediate. Sorry about that. Right. What do you think is going to happen to get me to the hemiacetal? Let me draw it first. How do I get from here to here? How do I get this proton on this oxygen?
Proton transfer.
Proton transfer, right? And it is, in this case, what we would call intramolecular. Intramolecular proton. Intra because it's, oh, I misspelled that, hold up. Intramolecular because it's internal. Everything is internal. If the proton is coming from an outside source, then we call it intermolecular. But in this case, it's intra. So this is just coming here like that, and then boom, this pair of electrons is coming here. It's that simple. That's how we get to the hemiacetal. All right. With the acetal part, excuse me, you don't start from scratch, right? This is 1 mole, all right? But you don't have to start from scratch to make the acetal. You start at the hemiacetal. Right, so to make the acetal, you actually start here. All right, so that plus another mole of alcohol. Right, so in this case, what happens in the first step is to do a proton transfer between the alcohol and this OH group here. So this is going to pluck that off. All right, and so what you end up with is an intermediate. That looks like this. plus that. All right. Now, the mechanism as far as how the acetal gets formed is actually kind of, there's a debate, right? There's a debate on whether, because there are two possible pathways. Right? In pathway one, you just lose the water, right? Spontaneously, kind of like SN1 type substitution. So I'm gonna put that here. So you lose the water and then you end up with an intermediate. That looks like this. And I know I'm cheating. Right, with a plus charge here on carbon. And then that is what the methoxy group will attack. So let me show you that. So this then just comes in and attacks, and you end up with your acetal. So that's one way to think about it. The other way to think about it is the methoxy group here actually forcing out the water. Right, so you do this and then that. Right, so that's the second pathway. We call that neighboring group participation. Neighboring group participation. And that happens a lot of times if you have a heteroatom that has pair of electrons next to a leaving group. A lot of times that heteroatom can force out that leaving group by just donating a pair of electrons. So you end up with an intermediate that looks like hold up 1 second. Like this. All right, and then this is what the methoxy group attacks. So this now comes here, like this, attacks, boom, and then that's how you get your acetal. I'm just going, well, I can redraw it. Right? So those two pathways for the acetal formation are both plausible. I mean, you can say that either one of them are possible because there's no impediment to either one of them happening. So me personally, I tend to lean towards the neighboring group participation pathway because there's no guarantee that proton, that carbon is going to be secondary like it is, but the neighboring group participation, it doesn't matter if it's a primary or a secondary carbon, because that once you make that pi bond between carbon and oxygen, then then you're good. Right? It doesn't matter because you're not making a cation. So I tend to lean towards that, but both are plausible pathways. So that's the extent of the reactions of carbonyls that we're going to talk about. So we talked about the Vidic, we talked about Hemiacetal formation and Acetal formation, and then on Monday we're going to finish all this up with imine formation and Gabriel synthesis, and then we'll be done. I haven't made a decision yet as far as whether we'll just take a 5th exam or take the final, but I'm actually leaning away from a cumulative final and more towards a 5th exam, but I'll let you know that on Monday. But that 5th exam we'll take it on the day of the final, but I haven't, I'll let you know on Monday what's what. Because with the way that the break fell, it just really it caused everything to just get squished into this last 3 or 4 lectures, and I don't like that. So we'll figure it out, but I'll let you know something on Monday. And I know some of y'all have reached out about your averages. I'll get back to you today about that individually.